Well, thank you very much. Well, it's a real honor to address the 10th anniversary of KIPAC. The first thing I'd like to do is to congratulate you folks. And I guess I have to wait for Roger to come back. But in any case, it's quite a feat to preside over 10 years of organized chaos that turns out to have very beautiful results. I put on the next slide just a few of the contributions of KIPAC to the study of dark matter. Of course, the bullet cluster, I guess Marusha is here somewhere. The stacked analysis of dwarf spheroidals from Fermi. This is some relatively new work from Risa Wexler and her crew on the relation between idealized dark matter halos in the galaxy and the presumably real dark matter halos in the galaxy. This thing down here is my little step into this. We'll talk about this just a little at the end. I apologize I didn't put CDMS up here, but of course CDMS long predates KIPAC, so maybe that's, these are more appropriate. In any event, what I'm supposed to talk to you about is theory. Dark matter theory is a very complicated business. And it's not a course, it's a half-hour lecture. So please excuse me if my remarks are a little disjointed, but I hope to at least amuse you and tell you a few things you didn't know before, I hope, about the theory connected with dark matter. People often talk about the dark matter problem. And one of the things that I, as a particle theorist, was a little surprised at when I started learning about this field is that different people think the dark matter problem is different things. Many people, of course, among you think the dark matter problem is how does dark matter exactly generate structure? Does it have to be cold? How does this work in detail? I'm a particle theorist, and that's not my point of view. My point of view is, what is it? And I like to say that the fact that 85% of the mass of the universe is not contained in the standard model is an insult to particle physics, which we have to do our best to remedy. Also, maybe I should say we'd like this 85% to fit in, if possible. It seems better to us if it has something to do with that 15% which we actually know something about. And this certainly colors our judgment, although maybe it shouldn't color yours. But it's definitely going to color this talk. So I just warn you to be aware of that. So the question that we're all asking, no matter what we think the dark matter problem is, we've been in KIPAC for 10 years and we haven't solved this problem, so why not? And how are we going to do it in the next 10 years? So in principle, there are a very large variety of dark matter candidates. And they're all attacked with different search strategies. And so to talk about theory, one maybe should address the wealth of these candidates. I'm not really going to do that in this talk, but at least I should start out by giving you some perspective. Among these candidates are some that I think are not going to be discussed for the rest of the afternoon, but they need to be pointed out as possible solutions to the dark matter problem. One of them is axion dark matter. The fact the axion is a very light particle associated with a field which is basically a macroscopic field in the early universe. At a certain point, it condenses out. As the universe expands, it's resolved into particles. Those particles have mass, typically 10 to the minus 5 eV is the number, but they're extremely cold. So they act like dark matter in the sense of providing the structure formation that you have in cold dark matter. You look for them in a very specific way that's adapted to this particle by conversion in a large magnetic field. It's some interesting news that an axion experiment, which has been running for a long time at Livermore, has moved to the University of Washington, and it's gotten a rebirth under the direction of Leslie Rosenberg there. And there are some relatively new results and a plan for the future that are given here. These acronyms are acronyms for different types of specific axion models. The lines correspond to axion densities, which would account for the dark matter density of the universe. And so we're actually going to know something about whether this hypothesis is correct within the next few years. Axions, I should also say, are an incredibly interesting dark matter candidate from the other point of view, which is astrophysics. Because they're so cold, and also because these experiments have the capability of vastly multiplying the strength of the signal. Once you know what the mass is, you just increase the Q of your cavity in which you convert them to increase the signal. They have the possibility of encoding the substructure of the galactic halo and giving rise to some very beautiful astrophysics. So if you're rooting for axions, it's a good time to root for them. But I'm not, so let's move on. Another topic, which I could devote a lot of time to, but I won't, is asymmetric dark matter. This is the hypothesis that dark matter arises in the same way that the baryon asymmetry of the universe arises, because there's some matter-antimatter asymmetry, and some matter is therefore left over when the bulk of this particle annihilates. If you tie the dark matter particle, that asymmetry, to the baryon asymmetry, you can rather naturally explain the preponderance over dark matter to ordinary matter just by saying the dark matter that particle's heavier. And so that leads you to searches in the low mass region, where you think about dark matter candidates that are, let's say, 5 to 15 GeV. The difficulty with this is that these models don't typically give you direct detection cross-sections. So that's a model building problem, which theorists can then try to solve to produce not only direct detection cross-sections, but the frankly rather large ones that are indicated by the signals that we heard about before the break. And finally, we can talk about primordial black holes, or compared to these guys, supermassive dark matter. And those are addressed with lensing searches, for example, macho searches. Overall, the whole range of dark matter candidates, I guess, spans from well below a micro EV to things that are maybe hundredths or tenths of solar masses. So it's a huge mass range. And now I'm going to just ignore the rest of it and concentrate on one little bit. So the part that I'm going to concentrate on is the one actually that got most of the attention also before the break, and probably also in the talks that we're going to hear after mine, which is the model that dark matter is a WIMP. Let me try and define a WIMP in a somewhat precise way, and I'm going to use all of the ingredients here. A WIMP is a massive, neutral, stable, weakly interacting particle, and this is very important, that was once in equilibrium in the early universe. So this is a very generic hypothesis, and yet it turns out to have very important implications, because from this set of assumptions, and you really don't need any others, you can get an approximate formula for the density of dark matter of these WIMPs today. And there's a very beautiful paper from the 80s by Mike Turner and Scherer that gave a very simple derivation of this formula, which gives the fraction of omega in dark matter in terms of the entropy density of the universe, the closure density, the Planck mass, some numbers that turn out to be of order 1, and the annihilation cross-section for these particles to annihilate in pairs. Actually, given that these numbers are order 1, we know all of the ingredients in this formula except for the annihilation cross-section. So you can just solve for that, and the answer to one significant figure is 1 picobarn. Now, this is a very interesting number because this is the size of a typical electroweak cross-section. And so this argument then draws the WIMP hypothesis, a purely astrophysical notion, together with a particle physics notion, which is we've got this question about weak interaction. It has symmetries. The symmetry is broken. We don't understand why that happens. There's this Higgs boson. We know it exists, but we don't really like any of its properties. Not even Mr. Higgs liked the properties of the Higgs. But we're stuck with it now. And so we've got to understand it. And so to tie those two aspects together is, I think, something that particle physicists, theorists especially, find extremely compelling. And so this leads us in a certain direction. But maybe I should say, you have to decide whether you, as astrophysicists, want to be led down this relatively narrow corridor through the entire space of models of dark matter. I should say that this picture does fit in the sense that I discussed before. We have many theories that give particles in the mass range of 100 to 1,000 GeV that satisfy these hypotheses. Although this specific estimate, well, the relation between this estimate and masses we're going to come back to. There are some complications there. There are implications of the WIMP picture, and I think it's very important to point out these are not shared by any other model of dark matter. First of all, what I've just stressed, the dual motivation. The dark matter particle has a raison d'etre which is independent of the dark matter problem. That's also true for axions, but probably not for asymmetric primordial black holes, etc. One species. In this class of models, it is very natural that dark matter is made of one particle rather than a collection of particles. There's a new quantum number in some new spectroscopy that explains other things about particle physics at the TeV scale. Whenever you make a particle in this sector, it decays to the lightest state. If the lightest state is neutral, it's also weakly interacting all the other hypotheses. That's the dark matter. As all of the particles in this TeV spectrum decay, the end point of the decay is the thing you end up with 85% of the mass of the universe. There are other models of dark matter, composite, various forms of asymmetric, hidden valley type dark matter that don't have this property, that have a much richer dark side spectrum. But once you buy into the WIMP idea, I think you have to buy this as well. And finally, complementarity. The fact that there are different ways of looking for dark matter, which in some way complement each other, come from the fact that the dark matter has some kind of weak interactions, has this particular mass scale. And so then the various direct, indirect collider measurements to get at dark matter fit together. That's not true with many of the other hypotheses. So really, if you like those three things, you run with the WIMP picture. But maybe I should also say, if you don't believe in the WIMP picture, you should be prepared to relax some of these other hypotheses. Of course, if you have a way to find dark matter and it succeeds, we're not complaining. OK. Often the WIMP model is equated with supersymmetry. And this shouldn't be done. Every model of the TeV spectrum has its own idiosyncrasies and really needs to be studied in detail. Supersymmetry appears because it's the one that typically people have done the most work on. And actually, because I'm supposed to show some of that work, that'll be reflected in the remaining content of this talk. I should also say that supersymmetry has more idiosyncrasies than most, but it also has some very beautiful non-dark matter implications. It's a weak coupling theory, extendable as high in mass as you want. It gives a natural grand unification. It's very beautiful in terms of its theoretical structure as an extension of space-time. And a lot of people like it for those reasons. Okay. One model that I should point out that's different from supersymmetry in some important respects is the universal extra dimension model. This has also been studied very extensively by K.C. Kong, Konstantin Machev, and various groups of collaborators. This is a model in which there are extra dimensions, where the Kaluza-Klein excitations, that is, the excitations with momentum in the extra dimensions, are new particles. The lightest particle of that type, the partner of the photon, for example, would be the dark matter particle. In that model, typically the mass of the WIMP, there is a WIMP, which is what I've just described. The mass of the WIMP is typically somewhat heavier than it comes out to be in supersymmetry, somewhere between 500 GeV and a TeV. I should also say that those models are under some stress, like supersymmetry from the LHC. In this recent paper, the yellow region is actually excluded at the LHC. The correct dark matter density is given by the green line here. So we still have a way to go, I suppose, in terms of the full coverage of the model. And this, the scale here has to do with the mass splitting among particles at the same Kaluza-Klein level. So when that's small, this model is hard to observe at the LHC. That's something called compressed spectrum, which we'll come back to in a little while when we discuss supersymmetry. Okay, so now let's talk about supersymmetry. Supersymmetry has pluses that I've emphasized on the previous slide. It also has minuses, which is that it was expected to already be found at the LHC and it wasn't there. And the natural WIMP cross-section is hard to achieve. And what I'd now like to explain is that these minuses are not insuperable. And so we can go on talking about supersymmetry and maybe learn something in the process. Here's the illustration one. I don't know. Theorists like to criticize other theorists. So it just gives me some gory pleasure to show these two slides together. This is the pre-LHC prediction of the expected region in a certain parameter space, M0 versus M1/2, for a certain class of supersymmetric models, put out by John Ellis and his collaborators at CERN. This is a 68 and a 95% confidence region. This, as of actually 2 years ago, was the exclusion. Below the line is now an exclusion from CMS. And since then, the exclusion is now, it more or less covers this whole region here. So where people on paper predicted supersymmetry to be, it wasn't there. Here is an illustration. I'll come back to this point and try and explain why. But let me just quickly talk about the second point, the natural WIMP cross-section. So here is a very interesting survey of supersymmetry parameter space done by Howie Baer, Box, and Summy. This is the omega h squared. But remember, it's also, if you look at point 1, that would be the annihilation cross-section in picobarns. So the magic value of the annihilation cross-section that you need to get the right dark matter density is the green dotted line. And this is a survey of supersymmetric models in a parameter space that these people did a computer scan over. It's very interesting. You see that you always miss with very high probability. Either the cross-section is over here too low or over here too high. Both of these facts are explainable, but to explain them, you have to go into a little more detail about what's actually going on in your model of supersymmetry. Supersymmetry here is not an exception. If you go into the other leading candidates for new TeV spectroscopies, universal extra dimensions, which I mentioned a moment ago, Randall-Sundrum, Little Higgs, as you explore the theory more deeply, you get these problems, that the theories have very large parameter spaces. As you explore those parameter spaces, you find exceptions. Eventually, there's nothing but exceptions. And nature only needs one solution, right? That's the one we live in. So it's very interesting to explore this. The explanation for this dichotomy is shown on the next slide. This thing here is a typical pre-LHC supersymmetry spectrum. In supersymmetry, you have a partner with spin differing by 1/2 for every known particle. So here are the partners of the W's, the Z's, the leptons, the neutrinos, the quarks. In this kind of a spectrum, the thing that is supposed to be controlled, that you really know where it is in terms of the physics that generates electroweak symmetry breaking is the Higgsino, the partner of the Higgs boson. Because the constraint of the theory is that it should generate the Higgs vacuum expectation value in the right place. Here, that's right in the middle of the spectrum. And so basically, it pulls all of the superparticles down to the point where you really ought to observe them. But this choice is just a parameter choice in a 20 or something parameter space that supersymmetric models live in. It corresponds, if you look at just the electroweak part of the supersymmetry spectrum, to something that looks like this. These are the Higgsinos, the partners of the W, the so-called Winos, the partners of the U1 gauge boson, the Bino. It's equally easy to have that part of the spectrum look like this. Then the Higgsinos are tied to a scale of a few hundred GeV, but these guys are untied. They can go up in mass, and the partners of the quarks can actually go up to multi-TeV without much harming the consistency of the theory. The things that are hard to raise are the third generation squarks, the top and bottom squarks, and eventually the gluino, the partner of the gluon. So in models that are more relaxed with respect to the LHC exclusions, those are the things whose positions you have to look for carefully. Now, depending on which of these models you choose, you get different sides in this diagram. If you have the Bino LSP, as it's called, typically you have very small annihilation cross-sections, so you overproduce dark matter. If you have Higgsino dark matter, you have very large annihilation cross-sections. The Higgsinos annihilate into W bosons with a big factor in front of the various alphas and pi's that come in the expression. And you get very small annihilation cross-sections. Sorry, large annihilation cross-sections, so small amounts of dark matter. But the real world is in the center. So if you believe in supersymmetry, you need some exception in one way or the other. And that exception can have interesting implications as far as both the collider searches and the dark matter phenomenology. Let me just show you a few glimpses of that. If you have the Bino-type dark matter, you need to somehow put more oomph into the annihilation process. And a way to do that, which seems accidental, but maybe it's required on the basis of what I've shown you, is co-annihilation. You bring another supersymmetric species down close to the Bino so that both of these guys are in thermal equilibrium at the time that dark matter freezes out. This guy does the annihilation, and what that requires is that it's within about 10 GeV of the Bino. That little mass gap has an implication for the LHC searches. It just liberates very little energy when the partner decays to the dark matter particle and makes the events much harder to see. And so in these co-annihilation scenarios, this is a plot from Atlas showing how as that mass gap closes up in a particular model. This is a suppressed zero. This is 20 GeV. You lose your sensitivity to the signature that's being searched for because that last transition gives rise to so little energy. In a model like that, you can have that second particle give all of the power of getting the dark matter annihilation cross-section right. Here's a model from the Chicago group giving some parameters for a model where a supersymmetric tau lepton next to a Bino gives the right dark matter density. On the other hand, if we go the other way to the model where this guy is the lightest supersymmetric particle, actually it can't be. We need something lighter to be the dark matter with a small mixing with this guy in order to weaken the annihilation cross-section. One thing that we can do is put the Bino just below the Higgsino. That's something called well-tempered dark matter. There are some other solutions as well. So we have the well-tempered neutralino. I'd like to say some things about its direct detection. And then maybe I should say those first. And then I could say, well, you can get away with pure Higgsino or even pure Wino dark matter, provided those states are very heavy. For the Higgsino, about 1 TeV. For the WINO, about 3 TeV. Here are those things I wanted to tell you about dark matter. The Higgsino cross-section in the limit where lots of supersymmetric particles are very heavy is very simple. The Higgsino goes through, it exchanges a Higgs boson with a proton, and that gives a cross-section which is essentially independent. That gives a cross-section which, for which basically the direct detection cross-section is independent of the mass of the Higgsino, just a constant value. That value is a very interesting one. 10 to the minus 45 is a zeptobarn. It's where we've almost but not quite gotten to with the big xenon experiments. Actually, this plot, which goes up to 200 GeV, this was made a long time ago by Aaron Pierce. It's probably something that most beautifully shows this phenomenon. But if you drew the xenon 100 exclusion, it would come down like this and eat up most of this plane. Here's another plot, roughly contemporary from Howie Baer's group. You can see this branch of the solution is the well-tempered neutralino, this Higgsino mixture. These lines down here with incredibly small direct detection cross-sections are the co-annihilation scenarios that I talked about a moment ago. The next group to try and come into this regime is Lux. And so Lux has the possibility really of identifying this out to high mass or excluding it totally. And we might even see that, well, within the next few months. I'm not sure when Lux is set to announce their first results. But the whole tenor of this talk could make a phase transition at that point. So we'll see what happens. For the high mass scenarios, there's some very interesting sensitivity in astrophysical gamma ray detectors. This is a new Hess exclusion of single photon lines. And very interestingly, it cuts deeply into this of order 3 TeV solution with a heavy WIMP. This is done by actually Tim Cohen, who's here, some collaborators, and Fan and Rees independently at Harvard. I should say that the prospects for supersymmetry, I'm, I guess, much more optimistic. There are much deeper searches for SUSY that will be made in the next run at the 14 TeV LHC. I think especially in the models with relatively light stop, we'll eventually get to gluino masses of about 3 TeV, which I would say almost covers the model space in which supersymmetry is relevant to electroweak symmetry breaking. Let me just show you this plot, which is the current exclusion from CMS of gluino production, where if there are light stops, the dominant decay mode is into TT bar neutralino. You can see it goes up already to something like 12 or 1300 GeV. In the next run, up to 300 inverse femtobarns will double that. And with another factor of 10 in luminosity, probably push that to about 3 TeV. So we're going to get tremendous reach in these most interesting SUSY scenarios in the gluino. If we find the gluino, then it's duck soup. You have this large energetic jet. You have a missing energy signal. You look at the little pieces that remain. They contain the dark matter particle and actually the rest of the light SUSY spectrum. Okay, I showed you that. Hopefully, SUSY will also have some interesting consequences at E plus E minus colliders. And it's very relevant to me that the prospects for the International Linear Collider are moving forward in Japan. The most recent milestone is the site selection, this beautiful site in the Kitakami Mountains, which are up north of Sendai. If you go into the Ichinoseki airport, you see signs like this from the local government. In models with light Higgsinos, an E plus E minus Higgs factory is also a Higgsino factory. And here are some of the signals one deduces for a photon plus a light Higgsino final state. In the very clean environment of E plus E minus colliders, these signals, as you see, appear well above background. You use polarized beams, so there are multiple cross-sections that you can measure. and each one gives you some detailed information about the quantum numbers of the state you're producing. And if, as I've said, there must be something below the Higgsino that it decays to, you can pick up those decay products too and get still more information. Well, a long time ago, with Ted Baltz and Marco Battaglia and Tomer Wizanski, we had some fun taking some prospective LHC and ILC results and trying to put them together and to predict dark matter annihilation cross-sections and predict the astrophysical dark matter density. Of course, all those models that we studied are ruled out today, but nevertheless, they remain as existence proofs that this can be done. And I think this dream is still alive, that we can do very intensive particle physics experiments, study dark matter and the supersymmetric or whatever model is connected with dark matter, both at hadron and lepton colliders, piece together the information and compare it to what we're seeing from the astrophysical experiments. So that's it. The dark matter problem remains, but I'm still very optimistic that it has a solution. And because I believe in WIMPs, that solution will involve the discovery of new particles at the LHC even in the next few years. And maybe we'll see the beginning of a concrete story of dark matter when you guys come back for KIPAC at 20. Thank you very much.
I think, Michael, that was a terrific talk, and it answered a lot of my questions. And it led me to believe that we know a hell of a lot less about how to look for dark matter than I thought before I sat down here. LHC is very nice because as far as asymmetric dark matter is concerned, it can find particle and antiparticle in dark matter, even if dark matter cosmologically behaved exactly like ordinary matter and all the antiparticles are gone.
No, wait a minute, Bert. But that particle has to have standard model interactions.
It has to have, depends on what its interactions are and what the cross-section is and all the rest of it. The other thing I'd like to say to the assembled audience is that what's been happening to supersymmetry over time is it's become more and more baroque. When supersymmetry was first postulated, rather simple versions of supersymmetry were postulated, which didn't add too many new hypotheses to physics. Physics has, I think, never progressed by making things much more complicated. But all those simple ones are pretty much gone, and they become more complicated. And so you guys who are doing all the experiments, don't pay too much attention to this narrow focus on supersymmetry, and do your experiments over a wider range, over the axion range, over the asymmetric model range, and so forth. But it was a very good talk. Anything that disabuses Bert of some of his still remaining prejudices, I'm happy to do.